So where are we now? Where have we been? Where are we going? Now, I've got answers. Well, I've got at least some answers for the OpenShift installer. I know what you're all thinking. Patrick, how do you know the future? Well, I hear almost every day, AI is the future. Future is now. Future is here, but it's unevenly distributed. But to be honest, 2 weeks ago, I had a completely different presentation in mind. I was going to give a deep dive into the internals of the installer. It's long overdue. I still hope to give that. That's certainly not going to fit into a 35-minute presentation. But maybe next year we'll do a workshop, I hope. It'll be useful to some people. But about 2 weeks ago, I started playing with some AI, and I'm going to sort of fold that into this presentation because I think that'll probably be more fun for you, more helpful for me. So today we're going to talk about the past of the installer, talk about some history and some fundamentals. We'll talk about some recent projects that have wrapped up, removing Terraform from the installer and replacing that with Cluster API, the current installer landscape with all of the different installers for OpenShift. And then, like I said, talk about some AI ideas. I'm curious, how many people have installed OpenShift? Okay, maybe roughly half. And how many people have used OpenShift? Okay, similar numbers. If you used OpenShift and not installed it, somebody else installed it for you. You get the idea. Somebody had to put it onto that hardware. Just go over some of the fundamentals here. OpenShift install is a client for creating OpenShift clusters. Users provide an install config. The installer then generates the cluster configuration that's used to bootstrap the cluster, all of the certificates, the kube config, the bootstrapping scripts. The installer can also, and what my team mostly focuses on, it does provision cloud infrastructure. So it'll set up everything, AWS, GCP, Azure, a lot of on-prem platforms. So let's talk about the history of the installer. I've been fortunate to be sort of a passenger on this for maybe the second half of this journey, but I give some overview, and if there are corrections, please let me know. But January 2014, that's the first commit into the CoreOS Tectonic installer. That's the beginning of the code base that would eventually become OpenShift install. For comparison, in September 2014, it's the first commit to OpenShift Ansible. That's the installer that we used for OpenShift 3. Very different approaches between those two different installation methods. In January 2018, Red Hat acquired CoreOS. That acquisition would provide several key features that would go into sort of foundation for OpenShift 4. CoreOS operating system, operator framework, and of course the installer itself. October 2018, IBM announces its intent to acquire Red Hat. Acquisition was completed in July 2019. June 2019, OpenShift 4.1 was released. That's the first release of OpenShift, and that had support for infrastructure provisioning on AWS, so the installer would actually set up the infrastructure. You could also install the vSphere and bare metal. Users provided their own infrastructure. 4.2 added infrastructure provisioning support for 3 more platforms, Azure, GCP, and OpenStack. August 2022, 4.11 was released with the final planned platform, Nutanix. At this stage, we don't plan on add infrastructure support for more platforms. Mostly we're using something called external platform, which doesn't provision infrastructure, but provides native CCM support, Cloud Controller Manager support, integration with the cloud once the cluster is up. On August 10th, 2023, HashiCorp announced a license change for Terraform. They switched from using the Mozilla public license to the business source license At which point we started looking at Red Hat. We started looking for alternatives as we found that license to be unacceptable for the product. The solution that we landed on, I'll talk about this more later, is Cluster API. 4.16, we moved 5 platforms from using Terraform to Cluster API. It's AWS, Nutanix, OpenStack, PowerVS, and vSphere, all in that first release using Cluster API. And then just a few months ago, with 4.19, we finished the complete removal of Terraform and replacing it with Cluster API. So I'm going to go over some of the design and fundamentals. This is sort of the precursor for what I was talking about, a light version of a deep dive. So openshift-install is a directed acyclic graph. So install thinks of everything it produces as assets, and we have high-level groups of assets. So we have the install config. That's what the users provide for the configuration of their cluster. The installer takes that user-provided install config and turns it into Kubernetes manifests. So those are produced, then the user can edit them. Those will go into the cluster itself. It's not all of the manifests that go into the cluster by any means. It's the ones that rely on user input. So it takes those manifests and bundles them into ignition configs. That's how those manifests actually get into the cluster, and then along with the certificates, the bootstrapping scripts, all of that stuff is bundled into the ignition configs. Now, some installation methods can stop there and take those ignition configs and do other things with them. But with IPI, you can also create the cluster, which means that the installer is actually creating that cloud infrastructure. Let me take a look here. So I have this is the actual asset graph that the installer produces. So, the resolution's not great. Let me zoom in a look. So this represents the install config. So these are things that the user would put in, such as the base domain, public key, is your SSH public key just used for debugging, the name of the cluster, your pull secret. It's a pretty small set of things, the minimal amount that's required. And then those are used to then go create other assets. So this, for example, is the bootstrapping script. We have all of these are the Kubernetes manifests we were talking about before. So this configures the SDN networking. This is specifically for the manifest.openshift. That's for clusters. The point really is that it's a directed acyclic graph. So if you look at it, you zoom out, pretty easy to get lost, but the design keeps it pretty manageable once you realize the underlying design behind it. So as I mentioned, the top-level groups of assets are called targets, and the OpenShift installer exposes commands. How's that? Let me zoom in a little. The OpenShift installer provides commands so that you can that exposes to users the assets that are created as a result of those targets. So in this, in this directory, I have an install config. I won't show it because it's got my pull secret in there, but so that install config already exists. I can run create manifests in the demo directory, and this will create the manifest. It's actually printing out all of the log lines for all of the assets that are being created. And then we have 3 groups of manifests: Cluster API, manifests, and OpenShift. Manifest and OpenShift, those are 2 different directories for historical reasons. They could actually be combined, and in bootstrapping they are. But we keep them in place for backwards compatibility. cluster API has been recently added. We can talk about that more in a moment. But just in these directories, you'll see the different, you have the cloud provider config manifest, DNS manifest. These are all manifests that are exposed to the users. Power users can go in and configure those if they need to make edits for the cluster they'll be creating. If you run the next command would be openshift-install create ignition configs. So it's going to take those manifests and then it's going to bundle them in to some different ignition configs here. So we have the bootstrap ignition config, master ignition, and then the worker ignition. Bootstrap ignition is the really interesting one. Oops, sorry, it's JQ. Oh. So this actually is a massive, massive file. So this lays down a lot of the assets that actually go on disk onto the Bootstrap node, which is used for bootstrapping the cluster. We run static control plane, run a control plane using static pods on the Bootstrap node. So you can see this actually just contains the path where we'll lay down this particular certificate. There'll be all the manifests that we created in the previous step. There'll be the bootstrapping scripts. All of this is exposed right here in the bootstrapping ignition. For the we also have ignition for the master or control plane nodes and the compute nodes. But these look a lot different. They've grown a little bit recently, but typically these are what we call stub ignitions. So basically this just provides a source pointing to the machine config server that says, hey, when you get this ignition, which we load directly into the VM user data, it says, go grab my actual ignition from the machine config operator, or machine config server, sorry, which is running here. So this basically just says, hey, here's the certificate, go grab your actual ignition from here. And so one of the guiding principles for the installer is we try to delegate as much as possible away from the installer itself to avoid the sort of monolithic installer. So we want to leave machine configuration as much as possible. We leave that up to the MCO. Let me check one thing here. Okay, cool. So all those targets are exposed as commands, and that's sort of the interface for which users can interact here. So moving on, after we get that those ignition configs, the installer can move ahead and actually provision the infrastructure for you. So the installer will set up the networking, such as the VPC, the subnets, the router, the route table, load balancers, the control plane VMs, the compute nodes. Those are all set up day 2 by the machine config or the machine API operator. Sets up the DNS, and for now we also provision some IAM credentials. Although we're really trying to get away from that. Don't really need. It's becoming unnecessary, and users don't really want us to be creating IAM roles. So as I mentioned, not only is the installer almost entirely built around Terraform, but as a result of that Terraform license change, what did I say, maybe about 2 years ago, we needed to rework the product based on that change. So we'd spent about 10 years developing Terraform scripts and so forth. So we were looking for an alternative, and eventually, after sort of arguing against the idea that we would create SDK implementations for all of these, um, Joel Speed created a POC that demonstrated that we could use the Kubernetes project cluster API to actually provision the infrastructure and basically use it as a drop-in replacement for Terraform. Now, I'll show a bit more about that in a moment, but we really liked the idea of moving to cluster API too. Not only did it provide sort of a uniform experience, which was one of the main things I was looking for, because my team works on AWS, GCP, and Azure, but we have a whole other team that works on vSphere. We have a whole other team from Nutanix, partner engineers, maybe not even Red Hatters. So we wanted to have this sort of platform that we could use, and Cluster API provided that framework. Not only that, it aligned the day 1 and day 2 machine provisioning. So we're using the same mechanism in the installer that we will be using day 2. We're still working on this MAPI to CAPI migration. And also, I liked how it exposed more control over the infrastructure to users. So I'm cheating a little bit, but during that manifests stage I showed earlier, it produces cluster API manifests. So these are the manifests that the installer populates. It defines the configuration that will go to the cluster API to create the infrastructure. Users can actually go in here and edit these. So it exposes the infrastructure configuration, perhaps the infrastructure as code, directly to the users. The guardrails come off. There's not as much validation if you do that. Let's see if I can pick a good one. I think this one will be. So here you can see this Azure cluster manifest defines, for example, the security groups and route tables. So you can go through here, and this actually exposes the API that users can use. We don't really expect users to use this a lot, but it's come in handy in situations when we're running CI and so forth. And users may actually make changes here. So that was another benefit, is it actually provided a sort of supported path for editing infrastructure, whereas in the past, users might actually build their own installer, edit Terraform code, and then, create a request, support exception request or something like that. Also, this allowed us to moving to a native Kubernetes project allowed us to sort of shift our focus to contribute more upstream, whereas most of our work prior to that was going into Terraform configs. This is the cluster, an outline of the cluster API project. So we only embrace a small set of this. So cluster API has a concept of a bootstrap provider, a control plane provider, which is Hypershift. The installer itself only makes use of this small set, the infrastructure providers. So what the installer does to use this is we run a mini control plane using imvtest. Let me start with what Terraform did. Terraform, so the installer is a big fat binary. It's almost a gig, and it embeds several binaries within it. So what we did before that was we used we embedded Terraform and all the different Terraform providers inside the installer. At runtime, we extract them into this directory, and then we use the Terraform exec command, and then that calls out to the cloud provider and creates all of the resources. We basically did the exact same thing with Cluster API, except we also bundled in a little control plane. So we had etcd, Kube API server, Cluster API controller, and then these specific cloud CAPI providers. So we do the same thing. We extract all of those out into the install directory. We use env-test to run a little control plane, and then it makes calls to the cloud and provisions your infrastructure. So it's kind of neat how it worked out to basically follow the exact same pattern. Switching gears a little bit, many of you said you have installed OpenShift before. That, to me, doesn't necessarily mean you used the OpenShift install directly. For example, if you need to install to on-prem, it's likely you might have used the assisted installer, which uses the installer under the hood, and many of these do. Sorry, you all can't really see this, for example, but this is a diagram created by Doug Hellman, I believe, initially. But it says, give me an OpenShift. But if you're a user trying to figure out, I want OpenShift, you do have to think about what kind of OpenShift you want. Do you want a managed service, in which case you would use Rosa if you're going on AWS, or Arrow if you're going on Azure? You know, when I say managed, that means you're delegating, you're getting the cluster as a service. You know, Red Hat itself is managing the cluster for you. If you're self-managing, then in that case, depending on how you're installing, you may use the installer directly. But you may use the assisted installer. If you're in a disconnected on-prem environment, you might use the agent installer, which is also in the install binary. But we have a lot of different ways to install. And we have a lot of different binaries that provide those installation methods. And I think that's an interesting case of Conway's law in action. I don't know if you guys know Conway's law. I do, of course, from reading his seminal paper, How Do Committees Event, in the Harvard Business Review. That's a joke. But it says organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. So it basically means, you know, to simplify, if it has a different team, you're going to get a different piece of software. Or as Eric Raymond says, Conway's law is the rule that organization of the software team will be congruent. Originally stated, if you have 4 groups working on a compiler, you'll get a 4-pass compiler. As Tom Cheatham put it, if a group of N persons implements a COBOL compiler, there'll be N-1 passes. Someone in the group has to be the manager. So I wonder, you know, is this a problem? Should we do something? I hear a lot like this is a problem. And it is. It's kind of a problem for users, but how do we solve this? You know, and the idea emerges, oh, we'll just create, you know, one installer that encompasses all of them. The problem is then you just get one more. So, let's talk about AI a little bit, because one of the things that I've been learning about recently, and I have about 2 weeks of experience really spending some time on this versus 6 years. But when I look at Model Context Protocol, you know, I see that this is something that enables LLMs and agents, or maybe creates agents, depending on how you look on it, but basically to tape together different tools. You know, combine all those different tools. So what I've been sort of wondering about is, you know, can we look at that diagram? And, you know, those are all different tools, but if we expose those all to LLMs, it can help guide users to make those decisions for us. So I got kind of hooked on this when I started playing with the Claude Code CLI, which I just found to be a really slick piece of software in and of itself. Just the experience. I mean, we see AI do amazing things every day, and I'm like, oh, cool. We got a command line interface out of that, but I think it makes sense. I'm a software developer, so I like stuff like that. But when I saw that, I needed to spend some time digging into that, and I wanted to know, how does Claude Code work? So I spent some time sort of reconstructing very, very basic version of the Claude Code CLI, and that gave me a reason to sort of play with the OpenShift installer as an MCP server. So the Claude Code is a CLI chat app, which is built with, it's a React app, which I typically think of React as a way of creating web pages. But using the Ink library, you can actually render, it basically renders a React app right into the CLI. So, I create a super simple prototype for this. Basically, all it is this React app. It's got an LLM agent. I used a pre-existing MCP server file system from Anthropic, and then I created super basic, this is like MCP servers for this dummy for the openshift-install. Where I see this going potentially is, like I said, we could expose more of these installers directly as MCP servers. This is a prototype and kind of a toy. The app itself, I'm not sure if it's actually necessary, but that's a way of playing around with it. And where I really see things getting interesting is not just for users using different install methods, but what if we start exposing more Red Hat tools? So CCO-CTL, does anybody use CCO-CTL here? It is something we're working on integrating back into the installer itself, but CCO-CTL is the CLI for the Cloud Credential Operator. So users use that if they want to put workload identity federation support, short-lived tokens in their cluster. So they need to provision those workload identity federation configs before the install. That's not important. The important thing is it's a very complicated process for users. The documentation's kind of hard to follow. And I see a lot of value here. And, I think this is something that AI could, pretty quickly make much easier for users to do. And even more than these Red Hat tools, eventually we could add an MCP server, something like Red Hat support. Your cluster failed. Let me open that bug for you. Make sure to include all of the logs, save users the problem of creating that bug. And what I'm really curious about is what happens if we start adding external tools? Like what if GCP, AWS, and Azure, if they get MCP servers exposed, we see a lot of use cases where people want to set up infrastructure in advance. And I wonder if while they're figuring out their automation, because the customers don't want to, I don't see them using AI in their pipelines. At least I don't see how we come into that. But in that exploratory phase, you could get direct integration into the cloud with agents either provisioning infrastructure before updating your install config, things like that. Or say your install crashed, you can check some quotas for you, try to troubleshoot why is your install crashing. Here's a quick diagram more of the app itself, just to explain the sort of authentication piece, because this, I think, one of the benefits of running the system locally has is so like I said, so here is the openshift-install MCP server. So this is super simple. It's just calling out the openshift-install binary in the path. And then the way the OpenShift installer authenticates is by using the Cloud SDK. So it can use the identity of the VM, user login, single sign-on. So the LLM itself should never actually have access. Those credentials never need to go anywhere near the LLM agent. We would need to make changes to sort of make workload identity federation first class in the installer. So there's no cases where the manifests themselves create those, contain those secrets to keep those out of the LLM. Let me do, like I said, this is sort of a prototype, but I'll just quickly show sort of that Claude code, that Claude clone using the MCP installer. So if I go in this is an empty directory. We have about 5 minutes left. So this is that MCP server from Anthropic. It shows that that MCP server only has access to this empty directory. So I can ask it to create an install config for me. It'll say, oh, I need to, well, hopefully, it'll say, so here it is creating one with just some examples. This is just purely Gemini. I did nothing here. Everybody wants me to always say, oh, can it create an install config? Gemini can create an install config pretty well. What we really need to do here is build out our docs and our examples and feed it with more data, because once you get into sort of advanced scenarios, it falls down. I don't want to really go through populating the install config, so I'll use this one. We've got a bad install config here. So I can ask the LLM, show me the contents of this directory. It'll say, oh, I found this install config. These are the things I can do with it. I can validate it. I can create it. So a window will pop up here. It's sort of like a debug window. This isn't the LLM. That's just tailing the installer logs. So I wanted to show the difference between what the installer shows and what the LLM actually shows. So in plain language, the LLM, so first of all, it called the installer running locally, and it says, this base domain field is invalid. And then it sort of explains what we need to do to fix it. Yeah, but that's basically it. Just wanted to sort of explain the tool convey. You could show kicking off another install, but it's basically the same concept. So yeah, I'll wrap up the demo, and I don't know if there are any questions.
Patrick,
Thanks.
do we have any questions for Patrick?
Like I did my job very well. Okay.
It's a very non-technical question. I understand that you wanted to kind of synthesize seeing the future, the AI and the current installer. So for a user like me, what does it get me?
Yeah, exactly. So this is one of the things I've been struggling with is why people are like kind of implying let's use the installer, or let's use AI for the installer. And where I see the real value is if we plug in other tools. Like I think right now we spend a lot of time making the installer super simple for super simple use cases. So in my opinion, it doesn't get much better than that. Like I don't know if you use the installer, but if you want to create a cluster, it just has a survey. It asks you a couple of questions. In my opinion, it's when you're going to get into more advanced scenarios, like you want to use workload identity federation, or you're trying to figure out how to automate integration with your existing infrastructure. For me, where I'm going to use it is where we're trying to install on GCP, and we want to pre-create the firewalls because our network admin team is not going to give us permissions to create firewalls. So we need to pre-create those. I don't want to go through and figure out every firewall that we need. I think if we can get AI to at least, I don't know if it'll create the firewalls themselves or if it's going to spit out a Terraform or other config that says, here's how you pre-create the firewalls. I think it's those sort of one-off bespoke scenarios where it's really going to give value is how I see it.
Any other questions?
Well, right on time. Thank you.
Thank you very much.